this is an example of a more complex problem where we have a metal sample and it's introduced into a colder cup of water, and the metal and the water reach a thermal equilibrium. And so, real quick, I'll draw what this looks like up here. So we've got, okay, so we have a beaker of hot water that we had the metal sitting in, and now we assume that that metal is hot. And then we take that metal out and we put it in an insulated cup with cold water. And what that metal does is the metal gets colder and the water gets warmer, and they reach a point in which the water's not going to get any warmer and the metal's not going to get any colder because they're at the same temperature, and we call that temperature thermal equilibrium. Alright, so let's look at a problem. We've got a specific heat of metal at 0.56 joules per gram degree Celsius. A sample of the metal is at an initial temperature of 98.75 degrees Celsius and is placed inside an insulated cup with 460.7 milliliters of water at 21 degrees Celsius. The metal and the water reach thermal equilibrium at 28.9 degrees Celsius. What was the mass of the original sample used? So the assumption that we have to make is that the heat energy that was lost by the metal is the exact same amount of heat energy that was gained by the water. Okay. And we know that Q equals mc delta T. So we can say that the M of the metal, the specific heat of the metal, and the change in temperature of the metal is equal to the M of the water, the specific heat of the water, and the change in temperature of the water. So now we need to go over here and define all those variables. So the mass of the metal, that's what we're trying to figure out. What was the mass of the original metal sample used? Our specific heat of metal is 0.456 joules per gram degree Celsius, because remember C values are that joules per gram degree Celsius. The change in temperature of the metal started at 98.75 degrees Celsius and went down to 28.9 degrees Celsius because that's where the thermal equilibrium was. So when I put that into my calculator, I get 69.85 degrees Celsius, and I want to pay attention to significant figures on this one. This has two places past the decimal, this only has one, so my answer only needs to have one, so 69.9 degrees Celsius is the change in temperature. Now I have the mass of water, and it says 460.7 milliliters, but remember, with water, only water, 1 gram of water is equal to 1 milliliter, so that's the same thing as saying 460.7 grams of water. The specific heat of water is 4.18 joules per gram degree Celsius, and the change in temperature of water, well, water started out at 21 and it raised up to 28.9, so I do 28.9 degrees Celsius minus 21.0 degrees Celsius, and I got 7.9 degrees Celsius. Okay, so I'm going to start plugging these things in. I'm solving for my M of metal, so I can rearrange my formula to solve just for this. So if I want to get M of metal by itself, these two things are multiplied by it, so I would need to divide to get rid of those things. And I would want to do it to both sides. Okay, so my new formula is M metal equals the mass of water times the specific heat of water times the change in temperature of water divided by the specific heat of metal and the change in temperature of metal. So I'm going to plug all of these things in. So 460.7 grams times the specific heat of water, which is 4.18 joules per gram degree Celsius. And the change in temperature of water was 7.9 degrees Celsius. And my specific heat of the metal was 0.456 joules per gram degree Celsius. and my change in temperature was 69.9 degrees Celsius. I'm going to put those numbers into the calculator. So 468. And I got 477.2869, etc., etc. Now for my units, I have grams on top, joules per gram degree Celsius on top, and degrees Celsius. I have joules per gram degree Celsius on bottom, and degrees Celsius. So I have one of these on top, one of these on bottom. They cancel. Degrees Celsius on top, degrees Celsius on bottom. They cancel. So I'm just left with grams, which makes sense because it's a mass. Now, I'm going to go through and figure out my significant figures. So here I had 4. These values, these specific heat values, don't count. Here I only had 2. So this number right here is going to be the one that dictates how many significant figures I have. So always go back and check your change in temperatures, because that's where you're probably going to drop down to 2. Drop down a significant figure. And then this one has 3, so I need 2 significant figures. So my answer is 480 grams. Alright, we're going to be doing some energy calculations. And our formula for when we're calculating these energy calculations is going to be Q equals MC delta T, or Q equals MCAP. So we need to know what each one of these things is and what units we're going to be looking for in our problem to fill it into the equation. So Q stands for heat energy, and we measure heat energy in joules or kilojoules. Most likely you're going to be seeing joules. M stands for mass, and we measure mass in grams. C stands for specific heat, or it could say heat capacity. And the unit for that is joules per gram degree Celsius. And then delta T is all one term, it's all together, and it means change in temperature. And you're going to be measuring that in degrees Celsius. And I always take the bigger temperature and subtract out the smaller temperature to find my change in temperature. So let's look at an example down here. It says the specific heat of a metal is 0.456 joules per gram degree Celsius. How much of the metal in grams is needed to release 8,560 joules of heat when warmed from 14.5 degrees Celsius to 35.6 degrees Celsius? So our variables that we know we're going to need are Q, M, C, and delta T. Okay, so my Q, remember Q that it is heat energy, and I'm going to be looking for joules in my problem. So I kind of scan through and I see, okay, there's 8,560 joules, so that's my Q. And my mass, it says how much of the metal in grams, so that's the part that I don't know. My C value is the specific heat, and it's in joules per gram degree Celsius, so the specific heat of the metal is 0.456 joules per gram degree Celsius. And then my change in temperature, I'm going to take the bigger number minus the smaller number. So 35.6 degrees Celsius minus 14.5 degrees Celsius. And when I put that in my calculator, I got 21.1 degrees Celsius. Helps to turn your calculator on. Okay, so my formula is Q equals MC delta T. And I'm not solving for Q, and Q is what I have isolated, so I want to rearrange my formula. What I'm solving for is M. I need to get M by itself. So that means I'm going to divide both sides by C delta T to isolate that variable. So M equals Q over C delta T. So now I'm just going to plug in my numbers. I have 8,560 joules divided by 0.456 joules per gram degrees Celsius and 21.1 degrees Celsius. Okay. And when I put that into the calculator, I got 889.66 grams. Now, when we look at units, we've got our joule on top, joule on bottom, Celsius on top, Celsius on bottom, and we're just left with grams. Okay? And it's in the denominator of the denominator, so that makes it go up to the top. Now, I want to put my answer in significant figures, and I only want to do significant figures based on measured values. So we measured the amount of heat, we measured the temperature. This is a value that's a constant, it's a given to us, so we do not include that one. So we have 3 here, and we have 3 here, and we have 3 here. We also want to check our subtraction problem and make sure that when we subtracted these two numbers, we did it with correct significant figures, and it still has 3. So my overall answer needs to have 3, 1, 2, 3. I look to the number next to it. It's a 6, so it makes that 9 go up. That 9 makes that 8 go up. So I have 890, the decimal point, grams. So that's how you do a basic specific heat calculation.